Okay.
So our next speaker is Rosario Fazio, and he'll talk about measurement-induced transitions in long-range spin systems.
Okay, so first of all, thank you very much for giving me the chance to speak here. So I will present some work which I've been doing in collaboration with there's so many people and over the last few years, and just to mention what I should not forget. So I think a lot of credits, most of the credits goes to them, and in particular, I will discuss about these two papers which have in common the fact that we discuss measurement-induced transition in the system with long-range interaction. So let me introduce the the topic of my talk. It's about many-body open systems, and since several years we have many different platforms where we can study this type of dynamics, be it in cavities, cavity arrays, or optical lattice trapped ions. This is just a cartoon of what I'm going to discuss. And in this category, I will also include gate models, gate dynamics with single site measurements, where recently a lot of very nice results have been achieved. So if for some reasons you decide to ignore the outcomes of the measurements, this essentially behaves like kind of open system itself. Most of essentially all of the cases I'm going to discuss are systems which are governed by a Lindblad type of dynamics. The first part is the unitary contribution given by the Hamiltonian H, and L is given by Lindblad set of operators in Lindblad form. And all the discussion here will come essentially because of competition between the unitary part and the Lindbladian part. This is not always the case, but in general, and the first part of my talk will consider the situation. Typically, the Hamiltonian will try to induce correlations among the components of the system, while the dissipation, if local, for example, will try to destroy those correlations. This competition between H and L, if you combine with the fact that you are going to consider a many-body system, may result in non-trivial critical phenomena. This phenomena will manifest in the steady state of the system. So this evolution, this Lindblad evolution, will eventually lead to a steady state. For the moment, it's not really important to specify which kind of state we are considering, but the rho S, the density matrix, may possess, in a sense, or may lead, sorry, to symmetry breaking. And in this case, depending on the couplings of the various terms in the dynamics, then there will be transition between phases with or without spontaneous symmetry breaking, and typically people refer to those cases as dissipative phase transition. These phase transitions are occurring in a state which is in generally mixed. So if I look at this density matrix, this is just a generic way of writing it. But what I would like to point out here, that this density matrix, this state will be in generally mixed, and it will be non-equilibrium. In a sense, this is a kind of different situation for other cases that we know, like zero temperature phase transition in the ground state or equilibrium phase transition, where in both cases, for different reasons, all the information is encoded in the eigenstate of the Hamiltonian. Both the probabilities and the state that diagonalize the density matrix are related to the eigenstate and eigenvalue of the eigenvalues of the Hamiltonian. Here, being in a non-equilibrium situation, essentially this connection is completely lost, and it might lead to new phenomena. In particular, the correlations that are contained in the steady states and the quantum the entanglement which is contained in the steady state, it will be in general not in relation one with another. So just for reference, I would like to point out that so if you take a zero temperature phase transition, essentially the correlation length which governs, so just take a critical point, which governs the diverging of the correlation length of various correlators is the same that will enter, for instance, in determining the properties of the block entropy, the entanglement entropy. Here, because of the non-equilibrium nature, this connection is lost. And in particular, if I want to study entanglement, then I have various choices. I mean, I may have a look at the entanglement contained in this mixed state, and there are ways to do it. Or, and this is what I would like to describe here, that is related to this whole discussion about monitor system. One should follow the evolution of single trajectories, and then I hope it's not me. Okay, and then looking at quantum correlation contained there. So I just mentioned quantum trajectories just to specify very briefly the connection with the Lindblad equation. So essentially, I can look at the density matrix as a set of individual process which leads to the interaction with the surrounding states, and if just let me just give you this very simple example just to fix the thing. So if I want to study the decay of a two-level system coupled to some outside environment, if I look at the density matrix, then essentially I look at the probabilities and I will get an exponential decay. If on the other side, I continuously monitor the system, then essentially dynamics is very much different. So I will keep seeing that the system is in the excited state, and then some random jumps will occur. But just looking at the average distribution of this jump, then I can reconstruct the exponential decay. So in the same way, I can look at the average, the evolution of the average density matrix, and this leads in the infinitesimal evolution equation to the Lindblad, or I can rather follow each jump individually, and then the dynamics of the state of the system will be just a sequence of smooth evolution for certain K0 plus random jumps that occur at given times. This is the dynamics I'm going to follow, and I'm discussing this motivated by, there are by now zillions of papers. I just listed I guess the initial papers on the topics, but also in the case I'm going to consider here of the Lindbladian dynamics, if I look at the competition between unitary and unitary evolution and jumps operators, then in addition to dissipative transitions, then I may have transition, and this was pointed out by these papers, on transition in the behavior of the entanglement. This is, I just use as a symbol description of I mean, what is contained here. If you just imagine an evolution in which there are entangling gates plus measurements of some sort, then because of the unitary evolutions, then you build up entanglement, and in the absence of any measurement, then you will lead to a volume law in the steady state. On the other side, if you start doing measurements on single sites, then you keep destroying the entanglement. This is essentially what the environment does in the Lindblad dynamics, and you tend to destroy this volume life. Actually, how it was pointed by this, all this list of long list of papers, there is this transition between volume and area law takes place as a critical phenomenon. Now, one last thing that I should point it out, that by looking at this, by this monitoring system, then we should look at different types of averages. So I can consider a quantum, given a given trajectory, I can look at the quantum average at that, for that particular trajectory, and I can look at the average quantity of a given operators, whatever, O, over all trajectories. Now, as long as O is an observable, these extra averages will give you the same result as just considering the density matrix. However, if you are interested in quantities which are nonlinear in the state, and the entanglement is one of those quantities, then looking at the monitoring system, monitored system, or just looking at the average dynamics will produce different results. Actually, the entanglement itself has to be only computed in the along given trajectory. So this was my introduction. So what what I would like to tell you. So we studied different models, two different models in which dissipative or symmetry breaking transition and measurement induced transitions take place, being interested in their possible relations. We were motivated by possible realization in experiments, and in particular, I will discuss the first case in which we have a long-range interacting spin system with local resetting, thinking that this has a possible implementation with trapped ions. So let's say we were much more optimistic when we started this work. Now, about the implementation, we are less optimistic, and I will explain you why. And then I will tell you, trying to overcome this type of problem, meaning the connection to the experiment, I will describe the dynamics of a cloud of atoms in the presence of collective decay, claiming that this is very nice example. Well, and also easy to realize in experiments. I mean, easy from theory's point of view. Okay, so the first model, we study a kicked icing model with resetting, which means we just, in the same logic as with this circuit, we consider a model in which we had the Floquet-like dynamics, in which we had the period over which the system would evolve unitarily, with interconnected by random Krauss maps at in a fraction of the sites, and the dynamics went on like this. So thinking to application to trapped ions, then the Hamiltonian is just a long-range interacting spin systems in a magnetic field with power law interaction between the spins. On the other side, the measurement or the Krauss map that we consider was that of resetting, because this is something which might be possibly easy to realize locally in a fraction of the trap. Essentially, the resetting is a map that either just leave the states to its value if it's, for instance, down, or just reset it to down if it's in up state. And this is done with some probability P. As I said, we study this particular model because both the resetting and the Hamiltonian interaction can be realized in trapped ions. Now, sorry. This type of dynamics has or may have long-range long-range order in the x direction if the alpha is sufficiently small, namely if the coupling is sufficiently long-range order. On the other side, for large alpha, we do not expect any symmetry breaking. On the other side, if we look at the range of the interaction and its impact on the entanglement, on the transition of the entanglement, we expect, or we know that it should be much less critical. So we just studied with various numerical analytical methods, and because of time, that probably I will go fast on that, but we just queued some indicators to first say the transition, the ordering transition, and the transition of the entanglement. And okay, I don't want to go into that, but this is the resulting phase diagram that we get, which essentially tells you that just consider a given value of the magnetic fields, then on increasing the fraction of sites where you have, when you do the resetting, then you will have a transition between a ferromagnetic phase and the paramagnetic phase. Now, it is can be understood why this lobe here, but let me skip this. There is another transition. That is a transition between volume law and, say, some area or subvolume. I mean, it's difficult from the numerics to specify this, which is, however, taking place in a much earlier, deep in the ferromagnetic phase. So if you look at the monitored system, you can distinguish a ferromagnetic with volume law from a ferromagnetic with subvolume or area law. Let's say the behavior, this is what I think it's expected. The system first loses its kind of entanglement, correlations, but still keeping correlation between the spins, and eventually at higher fraction of measurement sites, then it goes to the paramagnetic. Now, the value of the critical thresholds over which the system loses its order, either in spin or in the entanglement, strongly depends on the range of the interaction. The critical value drops down, and for short range, there is no ferromagnetic order here, while there is always a transition between volume and non-volume law. So as I said, we were very much motivated by this study because we thought it can be realized experimentally. I mean, we did this work with collaboration with Guido Pagano, who is doing experiments in trapped ions. But we realized that also this scheme has a common problem to all this, or to most of this type of dynamics, that is known as post-selection problem. So essentially, the point is as follows. I'll try to explain. In order to compute a given quantum average at fixed trajectory, then you should be able to reproduce the single trajectory several times in a many-body system. But the probability to have the same trajectory or given trajectories, k is like exponential of, so it's exponentially small with the system size. And so that's why the experiments are tremendously difficult. It is possible to find ways to mitigate this problem, and either by taking specific circuits and actually the experiments of Google, I think, follow this theoretical work by Politi and Kemani, or trying to, there were attempts to use some feedback dynamics. So in the last 5 minutes or so, I would like to propose not a solution to this problem, but a system in which this problem does not occur. So it's a cloud of atoms, which has a collective decay channel. So this system undergoes a measurement-induced phase transition. It does not have this post-selection problem. And most important, actually, it was already realized in experimentally. I mean, not in the monitor version, but we think that doing the monitoring is not difficult. So let me describe the system in a few minutes. This is just a cloud of n atoms, where each of the atoms is like two-level system, and J is total spin. So it's like you have a bunch of spin 1/2 systems, and they just decay through the total spin. The Hamiltonian is just a sum over independent omega SZ. Right? So it's just JZ times omega. So it's pretty simple system, and it has a phase transition between a normal and a time crystal phase. We studied this exactly this model also with Jonathan some time ago. And the transition is, so if you have omega 0, which fixes the splitting of the spin and kappa, the coupling to the path, it is exactly at omega 0 over kappa equal 1. Now, what we did was to study trajectories on this system, just to look at the entanglement and other various indicators. So let me remind you that in the previous example, I show you that the entanglement and symmetry breakings were occurring at different times. Now here, for reasons that I do not particularly understand, the system behaves differently. So first of all, this is the entropy, the block entropy of half of the spins as a function of omega 0 over kappa, so in the steady state. And you see that the entropy is essentially area law in the normal phase. Here is weakly dependent on the system sides, and there is this peak developing at the transition. And you see in the derivative, it's clear. And this anomaly in the entanglement is occurring exactly at the same place as the symmetry, the transition to the time crystal phase. Now, in the region here, the growth of entanglement scales in this weird way. It's just the log, so it's just exponent of, it's a power of the log of n. With this power being always smaller than 1, actually, it is 1 at the transition. This is the curve. This is the area law phase. And it is smaller than 1 in the whole region here. Now, of course, we are doing numerics, so I mean, you can always find something that at large system size turn out to be area. I don't know. I mean, we cannot have a proof, but up to 600 spins, you show that this behaves in this way. Very far from the transition, but this is very hard to say. It seems that the entropy starts to scale like the log of n, very, very weakly, dependent on the system size. And as I said, for this particular case, the transition coincides with the symmetry breaking transition. Now, and I think this will be the last thing I would like to say. What we like very much about this dynamics is that it's essentially post-selection free. Why? So first of all, since there is one type of jumps, essentially a trajectory is just the binary string. So in order to determine the probability to reproduce the same trajectory, you have to evaluate 2 to the power to the length of the string, which means that essentially the saturation time. So we just did some analysis of the saturation time. Let's say here is essentially constant, so we forget. In the time crystal phase, the time grows as the log of the system size. So again, here we just could do only numerical analysis, which means that essentially the overheads in the worst case, in this example, grows polynomially. So there is no exponential suppression as in the previous case. So given the time, I will skip, but we just did some analysis of the quantum state. I mean, on a different unraveling, we consider quantum state diffusion and study other indicators of entanglement transition. We just consider in particular Fisher information. And something which is important for experiment, we assumed also the case of imperfect detection. And again, this is Fisher information. We just see the anomaly also in the case in which there is no perfect detection of the trajectory. And I think I will skip this and go to the conclusion. So essentially, I describe you a model of long-range interacting spin system where 2 different transitions occur, separating as ordered from a disordered phase and a volume from a sub-volume phase. And then I will consider another long range, but now in the coupling to the outside world, which has the merit, in our opinion, to avoid this post-selection overhead. And here is the reference. Thank you very much for the attention.
Questions?
Model that you showed, the dissipative phase transition and the measurement-induced phase transition seem to be unrelated to one another, like they occur independently from one another. Do you know of a way to couple them somehow, so to make this phase boundary depend?
No. So let's say I understand better the case when they are related, because you can have a system which order, for instance, ferromagnetically, without any quantum correlation after all. So then you expect that it's easier for a system to order rather than to keep quantum correlation. For me, it's much easier to see when they are unrelated. In these last models, they are coincidence, but I don't know why. And I don't have any general idea why this is.
So I had a couple of questions. So the first part of the ECing. So if you looked at something like negativity for the dissipative phase transition, was it showing anything interesting, or just to go on this?
We did not calculate. So let's say the only thing I can say, but I'm not sure I'm going to give you a good answer, is that as far as I know, there is no systematic studies of entanglement properties like negativities at the level of density metrics for a generic dissipative phase transition. Okay. And so I don't know if by itself should be singular or something. With Cristiano Ciuti and his group, we did some calculation of the Fisher information for that, for a similar model, but we did numerically, and we see some kind of anomaly, but I think it's.
And in the second model, in principle for the dissipative phase transition and just the dynamics, you're looking at a collective spin. So this is an n+1 dimensional subspace of the 2 to the n. Yeah. So now for the calculations of the block entropy and stuff, is it still possible with just the n+1?
Yes,
okay. That's why you have 600 spins.
Yeah, exactly. So it's you manage to use still permutational invariance.
But then does sort of these scalings with n, how seriously, I mean, in the sense that, is there some funny business happening, because really you're sort of working with a very small subspace, but you're sort of, when you're calculating the entanglement entropy, you're sort of pretending that the system is like a 2 to the n, not pretending, but it is a 2 to the n. Does this sort of,
you can, so essentially, given the model, so you can work in that subspace, and actually the transition, not the time crystal, but the transition in the magnetization was observed experimentally. So they can work in that subspace. Let's say something which I should, so you see that when you discuss such a weak like log to some, you never know that you need probably 6,000, but this, we cannot do anything.
Hi, Saro. So just a clarification and then a quick question. Clarification is, in the measurement induced part, what are you doing actually? Is it a typical measurement record, or because if you average,
we just do an average over all possible trajectories.
Average over all possible trajectories. So could you comment, Saro, what is the role of the measurement record? Because if you take, you showed a measurement, a master equation with a Wiener increment, right? If you just average, if you take the stochastic average, then you should just get back the average.
Yes, exactly. But you cannot compute the entropy by just looking at the density metric. This will, I mean, you know very well. This will not give you entanglement entropy.
So what is the role of the measurement record? I mean, is there something funny happening in inducing the phase transition?
No. So just for instance, if you want to compute the entanglement entropy, then you have to do first a quantum average, having fixed the given trajectory. But fixing the trajectory means that you have to know the record, because you have to reproduce the same trajectories many times. And so it's an equivalent way of saying that you have to work at the fixed trajectory.
Okay, thank you.
Yeah, so sort of related question. I mean, like if I'm looking at a single trajectory, is there some sort of ergodicity? Like if I'm looking at very long trajectories, I mean, like if I start with the same initial condition but look at 2 trajectories, they would give me the same entropy, or they would give different entropies?
I would say that after many jumps have occurred, I would say that on average you should get the same entropy. So in this particular model, yes, I don't know if this is a general model. So I don't know about, for instance, computing the variance of the entropy, how it scales. I don't know. It's a good point.
In the first part of the, where you have this ferromagnet from volume law to area law. I mean, if one looks at the density matrix, it will be trivial in both the cases. I mean, instead of
no, the density matrix. So if you compute the entropy of the density matrix, this is what you're asking.
yeah.
So if you compute the entropy of the density matrix, it's always volume law, but this is not entanglement because the state is yes, but it's always volume.
Yeah, I see. But the dynamic. I mean, how does the dynamics behave for the two cases? In one case, the ferromagnetic correlations, I guess the volume law has to, is the time scale, is the dynamics different in the two regimes?
So let's say in the case we consider, so that part was done on a much smaller system size. We saw that the saturation was of the order of scaling linearly with the system size. But so if I can connect to this last thing, the other thing is that is important is that there the trajectory is defined by all possible jumps at different positions. So even if the saturation time is independent, which is not the case, you get an exponential suppression by the fact that you have to decide where the jump occurs. Okay, so this is a weird simple model in which there is only one jump. So you have this is essentially a zero-dimensional model. So that's why you have.
More questions? If not, let's thank the speaker again.
Sure.